All right, guys, welcome to lesson 3 of chapter 10. So last couple of lessons we did exponential growth and exponential decay. So now we're going to focus our efforts on the number e. So the number e is used in exponential growth and decay as well. So that's going to be a new base that you'll find out what it is shortly. But it's sort of like pi, so it's an irrational number. So we're going to introduce this by looking at the first example. All right, so you have $1 and you're getting 100% interest every year, which, just for the sake of this lesson, I put 100%, but you're not going to get 100%. But in this example, just to illustrate the value of E. How much will you have at the end of 1 year if the interest is compounded, and then you have several different amounts? So quarterly, monthly, daily, hourly, and every minute. So let's start with quarterly. So this is an interest problem and a compound interest problem. So remember that the formula for compound interest is, so we have A, let's change that to a different color. So you have A equals P, the principal, which is how much you start out with, in this case $1. You have 1 plus the rate of interest divided by the number of times you compound it, raised to the number of times you compound interest times the time, usually in years. So in order to do the quarterly, well, n is equal to 4, right? And monthly, n is equal to 12. Daily, well, you have n is equal to 365. You're compounding it that many times in 1 year. Well, hourly, for hourly, you're going to have to convert that to how many hours are there in a year. So if you do that, turns out, so if you have 365 days in a year, and each day is worth 24 hours, per day. Well, if you multiply those, so 8,760 hours. All right, so that's how many hours there are in a year, and then we can use that for n. So that'll be our n. For every minute, well, you're going to have to take 8,760 hours in a year, and then each hour is 60 minutes. So that's 525,600 minutes. So how many times you're compounding in a year for that case. So let's go ahead and plug in the numbers here. So you have $1, 1 plus the rate is 100% per year. So this makes it real easy, because if the rate is 100%, well, 100% as a decimal is 1. So this will be 1 over n is going to be 4 raised to the 4 times, and we're going to do it at the end of 1 year, so that means that time is 1. So times 1. All right, and then if you do this, you're going to get $2.44. Now if you do it for monthly, 365 times, and then 365 times 1 is that. And that'll give you $2.71. So this is the dollar symbol. All right, and then we have 1 times 1 plus 1 over, oops, I'm sorry guys, this should be 12. Went ahead there. This would be 12, then this will be the 365. When you do the 365, you get $2.71. My bad, guys. And then if you do the 12 months, then that would be $2.61. Then if you did the hourly, you would get $2.71, and then you would get, 0.8 of a penny, essentially. So not that much more. And then if you were to do every minute, then in that case you get $2.71, 8/10 of a penny, and 2/100ths of a penny. All right, so so notice what's happening here as you're going from that number to that number to that number. So as the number of times that we're compounding increases, well then this is approaching a value, right? It's approaching, you know, this 2.718 number. So if you keep doing this every second, you know, every millisecond, you eventually reach some limit, right? And you really can't go much over that limit. So, and this turns out this limit is the number E, and it's really useful for growth applications and decay applications. So this isn't a constant, it's an irrational number. So it turns out that this number is E. So what is happening to the amount over time as you compound more times? Well, eventually it reaches a limit, and you know, you can't really reach much more. So in this case, so as interest is compounded more times, so the amount obtained peaks at a limited value, or we should say limiting value. Limiting. The value is you're limited by how much more you can get. So this number, as we said, is if you keep doing this, you're going to get 2.71821828459, and it keeps going on forever, kind of like the number pi. And this is what we call the number E. So the number E is like the number pi in that it is irrational. Irrational means that you can't convert it into a fraction, because the numbers don't necessarily have a pattern. They go on forever, and there is no set pattern that you can use to write as a fraction. So that's what we call irrational. Remember, rational means fractional, which means can be converted to a fraction. This is irrational, so it can't be converted to a fraction. So it is essentially a number of exponential growth and decay. So it is a number that is used for these kind of applications. So we'll be using it a lot in this unit. So E is used when something grows continuously. So when you think continuously, think happening quickly, happening rapidly, doing it multiple times. Think every second, every millisecond, continuously. So we know that as we approach continuously, then we reach the limit E. So the formula for continuously compounded interest is different, because now that we know that it approaches E, then we have a different formula for compound interest when we are compounding continuously, and that's A equals the principal times E raised to the rate times time. Or think PERT. This will help you remember. So A equals PERT. All right, so for continuous compound interest, you use PERT. So for this example, in 1982, the population of Bora Bora was 42,000 people. Population grows continuously. If the estimated annual growth rate is 2.8%, what will the population be in 2015? So in this case, we have to figure out, well, how long is that between 1982 and 2015? So if we were to subtract those 2 years, we would get 35 years. All right, and that is our time, 35 years. So we got the time. We know it does it continuously, so we know we're going to use A equals PERT, P-E to the RT. The P is how much you start out with, which is 42,000 people. The rate is 2.8% or 0.028. So we can go ahead and plug in these numbers. Times 35. All right, so this you can actually do this on the calculator, because in the calculator there's actually a dedicated function for this, or you can type it in on the computer and it'll be able to calculate it for you. But you should be able to do this on a calculator, on the scientific calculator. So if you do this, you get 105,813 people. All right, pretty straightforward. So now for number 3, you're going to repeat what we just did, but different scenario. We are compounding. This time we want to do compounding monthly and continuously. So if we're doing it monthly, we're going to use the regular compound interest formula. So remember, the regular compound interest formula is A equals P 1 plus R over N raised to the NT. So again, this is your principal, how much you start out with. Your interest rate is R, and you got to convert that to a decimal. Move the decimal place twice to the left, so 2.065. Balance after 4 years, so T equals 4. In this case, for monthly, you're doing it every 12 times in a year, since there's 12 months in a year. So we have $1,500 times 1 plus 0.065 divided by 12 raised to the 12 times 4 years. So when we do that, we get $1,944.03. All right, so that's compounding monthly. If it's doing it continuously, that means we're going to be using PERT, A equals PE to the RT. So we're going to, remember, E is just a number, so you're not plugging in for E. E is like pi, a number. You're only going to plug in for P, R, and T. So we have 1,500 E to the 0.065, and then the time is 4. All right, so when we plug that in, okay, so let me double check that number just in case. 1,500 E raised to the 0.065 times 4. All right, so we get $1,945.40. So notice that when we're compounding continuously, we're reaching a limit. This is the limit. This is as high as you can go. You can't go more than continuous, right? You can do, you can do daily, you can do every minute, you can do every second, every millisecond, but you can't go more than continuously. So when you do it continuously, you get this amount, and this is the greatest that you can have, all right? Which is not that much more than if you did monthly. All right. All right. So now, just kind of dealing with E, you can simplify E the way you simplify any other exponential expression. E is just a base, all right? In fact, E is called the natural base. So remember, the base is like, the base is the number that has the exponent. So if you had 2 to the x power, that's your base, right? If you had e to the x, well, e is your natural base. And that's because it occurs naturally. So it occurs naturally in applications of growth, as we showed you earlier. So when you have e as a base, you could do you're going to do the same rules as you would for any other base, all right? So in this case, you're going to divide. So 24 divided by 6 is 4. And then remember, if you're dividing, you subtract the exponents. So you have e to the 8 minus 5. So you get 4e squared, all right? Remember, e is just a number, right? So if you plug this on the calculator, you're going to get a number out of this. And that's all we want. Just simplify. All right, for this one, remember your exponent rules. So distribute the -2 power to both of these. So that means multiply. So 2 will have a -2 power, and then multiply -5 and -2. So -5 times -2 is 10. Remember the old rule, flip and forget. So you're going to flip the 2 down and then make it positive. So we have the e is still on top, but the 2 flips down. and becomes positive 2. And then 2 squared is 4. All right, so for this, remember, we can split this up into square root of that, square root of e to the 6x. Square root of 9 is 3. Remember the whole power over root thing? So we got to do e to the power over index. So the index is an invisible 2 there. Remember, there's an invisible 2 there. All right, so we got 3 e to the 6 divided by 2 is 3. So you get 3x. All right, so that's how you simplify stuff with e. Now remember, so if we did take a square root, you can do the absolute value of this guy, but it's not necessary because e is always going to be positive because e can never be negative, right? So you can never get a negative from an exponential. All right, but I'll leave the absolute value there, but it's not necessary. All right. All right, so now when we graph, again, good old graphing, when we graph, we're going to do the same thing as we do with any other exponential functions. However, since e is kind of like pi, it's a decimal, you're going to need a calculator, right? So you're going to need to be able to calculate these values. Again, the numbers that we like to use are -2, -1, so we're going to use that here. So we're going to set the exponent equal to -2, -1, 0, 1, and 2. However, notice that the exponent is already x, so x is equal to -2, x is equal to -1. There's no need to solve this like we did in the other ones, all right? So we can simply just make x equal to those numbers. All right, so now we're going to plug in e to the -2, so we're going to do this. So y equals e to the -2, which is 1 over e squared, and then we're going to get a decimal from that. We can do this on the calculator very easily, as long as you know where the e button is, and I can show you guys, you know, when we do that in class as well. So 1 over e to the second, so you would get 0.135. So 0.135. Okay, so do that, and then we're just going to plug the rest of them on the calculator, and we'll get what those numbers are. So 368, e to the 0, e to the, remember, anything to the 0 power is 1. So if I do e to the 0, that'll just give me 1. So 1, e to the 1 power, well, we know e is 2.71828, so I'm just going to round it to 2.72. E squared is 7.389. All right, actually, yeah, I could leave it like that. So now we can go ahead and plot this. We're going to plot this the best we can. These are decimals after all. So when we plug in for -2, we got -2 and pretty small. 0.135 is very small. -1, 0.368, again, very small. It's less than half, but we're going to do the best we can. And then 0 and 1. 1, 2.72, so that's almost 3. And then 2, 7.389. So we got 5, 6, 7, between 7 and 8, so around there. And now we can go ahead and plot the graph, do the best we can. All right, so it increases there, and notice that it is approaching a horizontal asymptote. Remember that the horizontal asymptote is what it's trying to approach on that one side. So it's y equals 0. So it's trying to approach y equals 0. That's our HA. So we're going to do that at y equals 0. X-intercept, we haven't, well, there is no x-intercept here, so we can say none. It doesn't cross the x-axis at all. The y-intercept, it does cross. It crosses at, 0. It crosses at 0, 1, so y is equal to 1. That's where it crosses right there. The domain is all real numbers, so -infinity to infinity. There is no x value that you can't plug in. Intervals increase, so this is always increasing, so increasing from everywhere. the range, the smallest that the y value can be is 0 because of the asymptote. And it can't even be 0. So it has to be greater than 0. So from 0 to infinity. The end behavior, as x is going to the right, the graph is going up. So that means y is approaching infinity. So as x goes more positive, y goes more positive, infinity. And as the graph goes to the left, well then, as x goes to the left or more negative, then the y value approaches 0. The y value is going down to 0. As x approaches negative infinity, y approaches 0. All right, so there's the graph and those are the features. So notice that this is exponential growth because remember, we have e to the x. And remember from the other lesson that if the base is greater than 1, then you have exponential growth. But we know that e is 2.71828 ... So which is greater than 1. That means this is going to be growth, which makes sense because the graph is growing instead of decaying. All right. So now let's look at this example. Should be another graphing one. This one has some transformation in it. So we're going to describe the transformations. Again, just like anything, remember from the other lesson, it was a times base raised to the c x minus h plus k. So we got to figure out what the transformations are. Well, a is 1, so there's nothing, so there's an invisible 1 there, so it doesn't really do anything. But you do have a negative. So that negative does a reflection about the x-axis. We do have another negative here, and that does a reflection about the y-axis. The plus 1 in the inside shifts it left, so shift left 1. The minus 4 here shifts it down, so shift down 4. And we have one more transformation. So the 2 here horizontally compresses it. So horizontal compression by factor of 1/2. Remember, for horizontal compression, you always do 1 over the number. For horizontal compression and stretch, you do 1 over that number. All right, so now remember, we want the exponent to be -2, -1, 0, 1, and 2. So that's exactly what we're going to do here. All right, so we're going to figure out what x has to be to get those numbers. But since we're doing this on a calculator, you can just use -2, -1, -0, 1, and 2. So in the other lesson, I told you, we need to be -2, -1, 0, 1, 2. Since we're using a calculator, you can figure out what it is on the calculator and then do it. But I'm going to do it by hand so I can show you. All right. Okay, so we're going to take that exponent and set it equal to -2, -1, 0. So let's do that. So that exponent is -2, x plus 1. All right, and we're going to set it equal to -2 first. All right, so when we set it equal to -2 first, we're going to divide by -2, divide by -2. X plus 1 equals 1. Subtract 1 on both sides. So x is 0. So 0 is going to be our first number. All right. All right, so I'm going to erase this. So now we're going to, next we're going to set the exponent equal to -1. So if we set equal to -1, then we divide by -2, divide by -2, and we have 0.5. So then, because -1 divided by -2 is 0.5. Subtract 1 on both sides. So you get negative 0.5. Yeah, negative 0.5. All right, we're going to do one more. So now we're going to do 0. So then divide by both sides by negative 2. So you get x plus 1 equals 0. Subtract 1 on both sides, and you get negative 1. So we can kind of see the pattern here. So it's going by negative 1.5, negative 0.5 on each side. So that's going to be our pattern. All right, so now that we know what that pattern is, we can go ahead and plug it into the calculator and get those numbers. All right, so remember, if you plug this in, if you plug in 0 in, you're going to get, negative e, because you have the negative there. And if you plug in 0 into the exponent, you're going to get negative 2, 0 plus 1 times negative 2, and then you have minus 4. All right, so that's if you plug in x equals 0. And then we're going to get that on the calculator, okay? So I'm going to do all this on the calculator and get what those numbers are. So for x equals 0, negative e to the negative 2 minus 4. So negative 4.135. If I plug in negative 0.5, I should get negative e to the negative 1 minus 4. So I'm going to plug that in the calculator. Minus 4. So I get negative 4.368. If I plug in negative 1, well, I'll just get negative e to the 0 minus 4. I could do this one by hand because this is easy. E to the 0 is 1, so I have negative 1 minus 4 is negative 5. All right, and I'm going to continue doing this on the calculator, so I'm not going to write it out anymore. I'm just going to get the calculator value. So next one will be negative e to the 1 minus 4. Negative 6.718. And then one more. If I plug in negative 2, I get negative e to the second power minus 4. Negative 11.389. All right, so now we can go ahead and plug it in. So 0, negative 4.35. So that looks like that's our y-intercept right here. This is our y-intercept. So I'm going to go ahead and plug that in, put that in right now. All right, so now negative 4.135 around there. Then when we do negative 0.5, I'll try to zoom in on the graph for you guys just a little bit. Okay, that way you can see more or less where I'm at. Negative 0.5, negative 4.368, so a little bit below where we had before. And then negative 1, negative 5, negative 1.5, negative 6.718. Over here, should be negative 1.5, so let me put it a little bit closer. Okay, and then negative 2 and negative 11.389. So that's, and I'll just put it around here, just so that we can draw the graph. All right. So notice that this part right here is trying to approach negative 4, or you can look at this and that's telling you that your asymptote is negative 4. So I'm going to put the asymptote as negative 4, y equals negative 4 here. And that's because you can determine that without even graphing it because of that negative 4 right here. Okay. But we know, we can kind of tell it's trying to approach -4. And then we have this part going like this. It's going rapidly. It's going rapidly, dipping down on the left side. All right, so our horizontal asymptote is at the -4. So let me write this out. So we got y equals -4 is our HA, as you can see from the graph. Our x-intercept, so we have no x-intercepts here, so none. It doesn't cross the x-axis at all. The x-axis is all the way up here. The domain, we have all x's. You can plug in any x value and you have a point on the graph. So -infinity to infinity. So for exponential functions, you're always going to have, the domain being all real numbers. So you never have to worry about that. Intervals are increase and decrease. This is increasing. Although it is increasing slightly, it is still increasing. So it's increasing all the way up to from -infinity to infinity. Right? Even though it doesn't look like it looks like it's approaching something, it's still increasing because you can always get infinitely closer to -4, right? And then as far as our range, well, our range is going to be all the way up to -4. So if you notice the -4 here, that's red line. That's the maximum that you can be. You can't even be -4. So the highest that you can be is just before -4. So you have to be below -4, according to the graph, right? The graph is below -4. So we're going to go from -4, or we're going to go from -infinity, because the graph goes from left to right. The graph starts out at -infinity and then goes up to -4. Okay, you always read the graph left to right. So from left to right, it's starting down here, and then it's going up to -4. All right, so the end behavior. So as x goes more positive, as x approaches infinity, this graph is approaching -4. So y approaches -4. As x goes more negative, so as x goes to the left, well, the graph is dipping down to -infinity. So as x approaches -infinity, y approaches -infinity. All right, so that takes care of that problem, and that's how you do the graph and the characteristics. All right, so there's the graph. So I'm going to show you guys on, Desmos how this, looks like. So if you notice, this is how the graph of e to the -2 times x plus 1 minus 4 looks like. Okay, and notice that it's approaching the -4 over here, just like in our graph. Now, remember that the negative reflects it, right? So if you were to do the regular e function, just e to the x, right? E to the x, then you would have something that looks like that. If you shift it down, -4, then it goes down. If you reflect it about the y-axis, which is what we did, it looks like that. Then if you reflect it about the x-axis, right? Well, then it goes like that. So it starts from there and then reflects like that. And then if you, shift it, shift it by 1 to the left, well, it goes from there to there. So it shifts slightly. And then if you put a 2, if you stretch it, if you like compress it, horizontal compression, then look at that, the graph is getting tighter about the x. So those are all the transformations that we had going on in our graph. So I want to just show you visually on Desmos, just in case you wanted to see that. All right. Okay, so now let's look at another type of problem. So this is the last part of the video. So all we got to do is determine if we have growth or decay. So this is pretty simple. Again, remember that the base is called the natural base. So know that vocab term. It is considered exponential growth so now with these guys, remember that if the exponent is positive, then you just look at the base to see if it's growth or not, right? So if the exponent is positive in this case, well, in this case, the base is e, and e is greater than 1. So that means it's going to be positive, or growth. And if the exponent is negative, and you have a base of e, well, then it flips to 1 over e, and 1 over e is less than 1 and greater than 0. So that'll be a decay. So just remember the rules from before. So if you have 1/5 e to the x, well, the base is e is bigger than 1, and the exponent is positive, so this is growth. For this guy, we have the exponent is 3x, it's positive. The base is e, so that's growth. For this guy, you can remember the 1 over e, you can rewrite this as e to the -1, because remember, you can rewrite it backwards. So if you know that e to the -1 is 1 over e, then you can write it backwards as e to the -1. So in this case, this is the same thing as e to the -x, which is a decay, negative exponent. Or you can think of it as 1 over e is between 0 and 1. So there's a couple ways, different ways of looking at it. Again, we have a negative exponent, so that means it becomes 1 over e, which is a decay. This one, negative exponent, becomes like a 1 over e. So if you were to rewrite this, just so that you guys know, because you have a negative exponent, you flip the e down, so it becomes 1 over 3e. The e goes with the 3 on the bottom, and then it becomes positive 7x. And then you have the plus 5 hanging out there. But see, this base is on the bottom. So, or you can rewrite this as 1 over e to the 7x. And, e is 1 over e is less than 1. So that's a decay. All right, a couple of different ways of looking at it. I wanted to show you both ways, just in case. But that's all you got to do, guys. So hopefully you learned something from this video, and hopefully it makes sense. And good luck, guys.